Right, so this is almost the last section, but there is a small section about the Big Bang Theory right after this section that I want to talk with you. And other than that, this is the last main section that we are going to talk at the end in this course. And basically, we will be talking about cosmology. Now, when I use the term cosmology, actually, we have talked some of these things even before, but the idea is summarize everything here. And just to let you know that this is a very huge subject. So what we are going to do here is just touch the subject from the surface so that you will have a basic introduction about this section. And then after that, whenever you need to, learn a little bit advanced things. So I hope this will help you, right? So that is the idea. And even though I told you like this will be a very introductory one, still I will go through some of the applications and some of the derivations that we can do to a certain extent. Now, when we define cosmology, cosmology is usually is a subject that we talk about the nature, evolution, and the origin of the universe, right? And now to talk this, now the structure, if I explain about what kind of scale that we are talking, now we have been talking about stars and then galaxies, the planets, stars, galaxies, and also about galaxy clusters, right? Now, all of these different phenomena that happen in these systems, actually we can talk all these things using Newtonian theory if we need, right? But if we, consider the current known structure of the universe, all these systems that we talk, like solar system, galaxies, even galaxy clusters, they seems to be very small if you compare the current structure of the universe. And excuse me. Now, when we go into this cosmological scale, what we consider is a very large volume that we can tell that the ratio of the mass to size of that particular volume increases. So the idea is we are going to talk something that is beyond even galaxy clusters, right? So I will just show you the scale of the universe that we are talking during this lecture. But that's the idea. Now, when we go for the large scale structure of the universe, you cannot use the Newtonian theory, right? Which is the normal gravitational theory that we use even to explain, the motion of the planets. And even you can talk about galaxies using Newtonian's theory without much of a problem in most of the cases. And also there are certain things that you can talk about even galaxy clusters. However, when you go into this cosmological scale, which is the scale even beyond the galaxy clusters, then you cannot use this Newtonian gravitational theory to talk about this cosmological scale. The reason is actually when you go into this large scale, the ratio of the mass to size is increases, right? What that means is we are going to talk about the effects coming from these huge masses, the huge structures. And because of that, you have to move into this theory of general relativity, right? It will become an essential theory in that framework. So that is the idea. So I have not written that here, but so this is why so what I have explained to you is what is cosmology, and why we are studying it, and why we need the theory of general relativity to study this subject, which is about the nature, evolution, and origin of the universe. So this is basically because the very large structure that we are going to talk about in here, right? So it is not about stars, not about planets, not about galaxies, or not about even galaxy clusters. It goes even beyond that, right? Now, when we talk about this cosmological scale, so I am going to give you a very brief introduction about this subject here, and I am going to start that by giving discussing you about these 4 key observed properties in the universe, right? So these are the 4 observed properties that we can get an idea about the subject. And those 4 observed properties are: number 1 is our dark night sky, and the second one is the cosmological principle, which is very important. And then the third one is Hubble's law, which we already have discussed to a certain extent. And if you were in this last few general degree lectures, you already know about this thing. And then the cosmic microwave background radiation. Right? Now, all these four properties are actually observed properties about our universe. So we are going to use these observations to talk about the cosmology, or the large scale, or the nature of this large scale structure of the universe, right? So we are going to start from the observations that we have, and then we will move on to the theoretical part that we can use to explain these observations, right? So that is the idea. So these are normally considered as 4 key observed properties of the universe. Now let's go through one by one and look at what are those, right? Right. So the first one is the dark night sky. And the idea is, now if you go outside and look at the sky, all of us know that the night sky is dark, right? Nobody used to tell the night sky is bright, no. So normally this is what we will observe if you go outside and look at the sky even now, right? Now, however, this observation that we have about the night sky conflicts with most common assumption of the infinite static universe. Normally, we now know that we are not living in a static universe, but we used to have this assumption, even if you remember that this is how even Einstein thought in 1916 when he was developing his general theory of relativity. Remember that I told you this story that he initially had his equation and then put an extra term to make the universe static at that time, right? So this is what people thought at that time, a static universe. Now this contradiction, which means we see that sky as the night sky is dark, and at the same time our observations conflicts with this our observation conflict with our common assumption about the static universe, and this contradiction with these 2 ideas is known as Olbers paradox. Right? Remember that paradox is something that, for example, you have learned, I hope that you probably have learned about the twin paradox in special theory of relativity, right? So this Olbers paradox is something like that. Now, if I explain this little more, the idea is if we assume that there are infinite number of infinitely old stars. Let's say we assume that There are infinite number of stars in the universe, right? Now the idea is, if that assumption is true, then what will happen is every line of sight should end up at a star. So that what that means is, at any direction when you are looking at, you should see a star, right? So that is the idea. If you have infinite number of stars, now then again, if we have a star at any direction when you are looking at, the light from that star should have a sufficient time to reach us, so that if you are living in the idea is, if you are living in a static universe, this the light that come from that particular star should have a sufficient time to reach us, right? So hence the night sky should be bright as the surface of the average star. So what that means is, if this is true, then when you look at the night sky, the sky should be bright as the surface of the average star. So at any time when you look at uh, the sky will be bright as a surface of an average star. So that is the reason, because when you, if the universe is filled up with infinite number of stars, and if the universe is static, then what you should see is, for every line of sight, for any direction that you are looking at, you should see a star, right? So that means that light should come to you, and then the night sky should be bright, and that the brightness should be equivalent to the brightness of average star, right? So that is the idea that they had. However, when you go outside and look at the sky, you see a dark sky, right? So this is what they called as the Olbers paradox. And now we know that the reason that the night sky is dark is because the universe has a finite age. We now know that our universe is around 13.7 billion years old. So that's a finite age. And also we know that the universe is expanding as well. And due to the fact that universe is expanding and it has a finite age, what would happen is, uh, the light from these distant stars hasn't had time to reach us. So they have not reached us. And also because the universe is expanding, the light coming from those stars are redshifted, so that you will not see those, right? So that's the first observation that we had about our dark night sky, that is related to the cosmology, right? And let's go into the second observation, and this is the most important one for us throughout this lesson, that is called the cosmological principle, right? And this is the second observation. And what that observation tells us is, on a sufficiently large scale at any given time, the universe looks the same to all, regardless where they are, right? So that means for a very large scale, and here it tells for a sufficiently large scale, at any given time, the universe should looks like the same to everyone, regardless of where they are. So that means the idea is that we are not in a very specific location, right? Everybody else, for anyone else who is in a different location, the universe should looks like the same. So that is the idea. And so this is what we basically call, this is the basic idea. And if we describe this furthermore, the cosmological principle is normally explained using these two terms. That is, the universe is homogeneous and isotropic, right? Homogeneous means uniform throughout the space, right? And what that means is, the number of stars per unit volume are roughly the same everywhere. So that means regardless of where you are looking at, if you take a unit volume, you will have the same number of stars, right? So that's what homogeneous means. So that basically tells us the universe is uniform throughout the space, right? And the second one is isotropic. So isotropic means it is uniform in all directions, right? So this is what we called as the cosmological principle. The universe is always homogeneous and isotropic. And this is one of the main observations that we have in cosmology, and all the mathematical concepts that we develop in this section will be based on this idea called that the universe is homogeneous and isotropic, right? For example, we are going to make or define a metric called a Robertson-Walker metric, and later in this chapter, which will explain the universe, and that metric is defined based on this principle called cosmological principle, which means assuming that the universe is homogeneous and isotropic, right? Right now, if you actually think about this principle, the universe is homogeneous and isotropic. It is very important that you should apply this principle to the large scale structure of the universe, right? Otherwise, you will get into a lot of questions, because if you let's just consider our solar system itself. Now, is our solar system is a universe and isotropic? So it is not, right? Because if you know that the sun has a specific location and there are planets going around it, so it is not uniform throughout the space, or not looks like same in all directions, right? The solar system is different, right? Because of that, we cannot tell that our solar system is isotropic or homogeneous. That is wrong, right? So that's why I have mentioned here, our solar system is not either isotropic or homogeneous. Right, so those are the, so that is one thing. Now let's go into the next scale that we learned. So that is our own Milky Way. Now our own Milky Way has a large concentration of stars towards the center of the disk, right? So if you remember, we had a separate section that we talked about galaxies and specifically about the Milky Way. And we remember that we talked about the structure and different parts of the Milky Way. Now, if you remember that, we have separate parts in the Milky Way, and there is a large concentration of stars toward the center of the disk. Remember that there were three sections like disk, bulge, and halo for a galaxy, and we have large concentration of stars towards the central region of this galactic disk. Now, what that means is our Milky Way is also not isotropic or homogeneous, right? Because you can see that the concentrations are different, so that you cannot tell that it is uniform throughout the space, so it's uniform in all directions. That is wrong, right? And then if you go into the next level, so that's about galaxies and clusters. Normally, what we know now from the knowledge that we have about the astronomy is that galaxies normally tend to be clustered into different, as different units, and these are called galaxy clusters, or sometimes they are grouped into different units. So we used to call them as groups. right? Normally we have galaxy clusters and groups in the universe. For example, if you think about the Milky Way is called as the local group where we have 40 galaxies clustered together. Like that, you have also galaxy clusters, and for example, so there is a galaxy cluster called Abel 426. So that's a galaxy cluster, which means collection of large number of galaxies together. And also, if you look at now, these entities are also not isotropic or homogeneous, right? Because they are, clustered together in certain regions, and there is a certain region, so there are no clusters like that. So you cannot tell that scale also, sorry, you cannot tell that scale as isotropic or homogeneous, right? Now, if you go into the next level, which means the cluster of galaxies, they form actually superclusters, which are separated by vast empty regions called voids, right? Now, even in this large scale where you have superclusters, still superclusters are more dense compared to the voids, right? So void means these empty regions between superclusters, right? And because of that, even in that scale, you cannot directly tell that the universe is isotropic or homogeneous. You actually have to go into the next level. Look at this whole structure of the universe as a single unit to tell that our universe is homogeneous and isotropic, right? So make sure that you get this idea very clearly, because even this is not only uh, uh, important to know for you, and at the same time, if you are going to explain this to somebody else who doesn't know much about the cosmology, these are questions sometimes you also get from them. For example, when you tell universe is isotropic and homogeneous, one could directly tell that how can you tell it? Even if you look at our solar system, it is not isotropic or homogeneous, right? Now, therefore, make sure that you understand this concept very clearly. The isotropy and homogeneous universe means this applies for the very large scale structure of the universe, right? Not for these individual, entities like solar system, galaxies, or galaxy clusters, right? So it goes even beyond that. And uh, there are actually evidences to tell that our large scale structure or our universe is isotropic and homogeneous. And these evidences actually come from, number one is using large galaxy surveys. Now, you may be wondering what uh, did I mean from large galaxy surveys. So I will give you a few examples for these large galaxy surveys. Now, if you consider the large scale of the universe, which consists of these superclusters and voids, we could observe this large scale through these large galaxy surveys, right? For example, Sloan Digital Sky Survey is one of the very famous and very popular, and also a survey that we have in very recent time, right? And the second one is 2-degree field galaxy survey. So that is also an example. Now this Sloan Digital Sky Survey is a very new one that took data in this past decade, from 2010 to 2020. And this was actually when I was learning cosmology. This Sloan Digital Sky Survey was not that much popular. Even it was not there, right? Now, the advantage of these surveys is that when you go for these very large scale galaxy surveys and map all the galaxies, then you can directly tell that the universe is finally becomes homogeneous, right? Now this is a map generated from this particular survey called 2-degree field galaxy survey. And you can see that you have supercluster structures and voids here. But if you go for one, the idea is if you get, sorry, if you get, yes, right here. So I'm wondering whether you can see my shared screen still, or you cannot see it. Right, so to make it safe, let me stop share and share the screen again. Right, so I assume that all of you can see my shared screen, right, with this map of 2D field survey map. So if not, please let me know. Right. You can see that if you take a small region of this map, you cannot tell that the universe is isotropic or homogeneous, right? But however, you can tell that universe is isotropic and homogeneous if you look at the large scale of that, which means the whole map, right? You can see that even if you look at in each direction, it looks like the same, right? It will be the same kind of structure in everywhere, and this is what we called as the large scale structure of the universe. And just to give you a little bit more detail, here is where you have our own Milky Way. And if you go along this line, you can see there is a small number mentioned here, 0.05, 0.1, 0.15, and 0.2. And these are actually the uh, redshift values, different redshift values. And if you remember that, if you know the redshift value, you can actually find the distance to that particular galaxy or galaxy cluster or to the supercluster, right? And the distance in terms of light years, billion light years is given here, and roughly it goes up to 2 billion light years. So that's the capacity of this particular galaxy survey, right? Now, according to the cosmological evidences that now this is an example that what are galaxy surveys and what is the advantage that you have from these galaxy surveys to understand that our universe is homogeneous and isotropic, right? So this is a very nice example for that. Now, according to the cosmological evidences that we have, the average density of the stuff contained in a sphere with radius of 100 megaparsecs is same in any other sphere in anywhere with the same size, right? So the idea is, if you consider a sphere of 100 megaparsec, and if you go to a different region of the universe and take a sphere with same radius, which is equal to 100 megaparsecs, then the things that contain inside that sphere will be same, right? Now it is this structure, which means the scales around 100 megaparsecs that you have to tell that the universe is isotropic and homogeneous, right? You can clearly see that it works only for this very large scale structure, right? Uh, so that is the first evidence that we have to tell that the universe is isotropic and homogeneous. And let me show you at the same time, because this may be important for somebody who is interested in astronomy. and research in this area. What are these surveys and how they looks like. So let me just give me a minute. Right, so let me go into a different window here. So let's go into this Sloan Digital Sky Survey. So this is the web page of the Sloan Digital Sky Survey, which is one of the largest galaxy surveys. If anybody is interested, I am going to post the link as well. And what this actually does is, you can see that this is the main web page. So their latest data release of this galaxy survey is data release 16, and it is interesting to note here that the final data release of this Sloan Digital Sky Survey is scheduled for December 2021, which is a few months from now, which is very interesting for me, for anybody who is doing research in the field of astronomy, to keep an eye on this new data that comes in from these large surveys. Right. So what I want to tell here is this is what we called as the Sloan Digital Sky Survey. Now you can see that the first front image here in the website is the Sloan Digital Sky Survey mapping the universe. So the idea is to map the universe from the data that we are getting here. So they have a section for the data right here. If you go there, you have all the details about the data that they have. Basically, they have data about millions of galaxies, and some of them have just imaging data. That means you can take images of these galaxies for different research purposes, those kind of things. And they have a separate section called K.V.S jobs, where even you yourself can go there and make an account, and then after that you can download any kind of data that you need, and this is completely free for anybody in the world. So that's the normal policy in most of these data that you have in astronomy, not like the other research areas. Anybody who take the data, you have to release all this data to the public after 18 months, so that somebody else can use that data, right? And also they have optical spectra for different galaxies. So like that, there are large number of data products here for that you can use for different purposes. And I have mainly used to get some of the data about galaxy clusters here for my research. And so I just need to show you what kind of website it is and what kind of things that they have doing. Basically what they are doing is they have this telescope right here, which you called as the Sloan Foundation 2.5 meter telescope at Apache Point Observatory. And this is in southeast New Mexico, right? So that is where this particular telescope is located, and it has details about the secondary mirror and everything, which I guess we talk some of these details about the chapter that we had telescopes at the very beginning, right? So they use this telescope with 5 filters. So what the telescope does is, in each night it start taking data. So it over the time it kind of scan through the whole sky and take look at different galaxies, galaxy clusters, and take all this data And so at the end, you can make a very large map, right? So that's the idea. So let me come back to the presentation here. Right. So those are what we called as large galaxy surveys. And actually there are some other surveys. For example, this 2-degree survey, and there is another survey called PAN-STAR or Pencil Star survey, which also have large number of galaxies and data for those, different magnitude values for those galaxies. And all of these sky surveys are completely free to access for everyone. And that's what actually we are using for our research as well. That's the nice thing actually about, astronomy research. You don't need to, you don't even need to go and access a telescope, because most of this data will be released publicly after some time. Even for the Hubble Space Telescope, it is the same policy. You can access those data, right? So that's something extra that I'd like to mention. And now the second evidence that we have to tell that universe is isotropic and homogeneous is this. So we are going to use the same survey, 2DF survey, which is devoted to quasars, right? Now remember, I told you what is a quasar in last lecture, at the end of the last lecture. So that is because specifically I have to mention about quasars here as an evidence for the homogeneous and isotropic universe. So the quasars are active galactic nuclei with exceptional brightness. Remember that I have mentioned this in my past presentation. And they basically arise by releasing the gravitational potential energy by matter falling into supermassive black holes. These quasars are in galaxies, especially these are like very active galactic nuclei. And these are formed by, by releasing gravitational potential energy by matter that are falling into supermassive black holes. Supermassive black holes are at the center of galaxies, right? And if you look at in a large scale about the distribution of these quasars, what you can see is that the quasars are distributed isotropically around the Milky Way. So which means from the Milky Way, when you look at and make a map of all these quasars, and this has also done using this 2DF survey, what you can see is quasars are distributed isotropically around the Milky Way. So which means in any direction that you look at, you will see, the quasars looks you will basically see the same distribution of quasars, right? That is the idea. And because of that, you can tell that if you assume that there is nothing special about the location of our Milky Way, we can assume that quasars are distributed isotropically about all points, right? And this is one of the strong and sufficient evidence to state that these quasars are also distributed homogeneously, right? So it's basically that is the second evidence to tell that the universe is isotropic and homogeneous. And here is the third evidence that we have to tell that our universe is isotropic and homogeneous. So that is based on these observations of cosmic microwave background radiation. And this is in short, you should tell that CMBR. And if I, does anybody know what is cosmic microwave background radiation? Anybody have any idea about it? Right. If you don't know about it, So I have basically talked about this in the general degree lectures as well. Now, in the last section of this chapter, we will talk about the Big Bang theory, which is the current standard theory that we believe as the beginning of the universe, which basically explained that there is an explosion, and from that explosion, everything started to expand, and then we are initially there were only subatomic particles, and then they move on to make hydrogen and helium. Like that, it developed, and then you have these galaxies after that, galaxy clusters like that, right? And during this process, there is a time short after the Big Bang that we believe that the universe became opaque, right? And at that point, so I will explain this a little bit more at the last section. So there is something called a thermal radiation that we believe that emitted at that point. That thermal radiation should be uniformly distributed through the universe, right? Now the idea is when we detect, if that is true, we should be able to detect that right now. And according to the Big Bang theory, the temperature of this cosmic microwave background radiation should be around 3 Kelvin, and I guess it's around 2.7 something Kelvin right now. And the idea is, when the universe get expanded, these cosmic microwave background radiation should be redshifted, and because of that, we should detect those radiation as microwaves now, right, in the microwave region. And I will actually explain a little bit more about cosmic microwave background radiation later. But the idea that I want to convey here is that when we look at this cosmic micro background radiation in the universe, we can make this map right here, right? And this map is actually basically shows you the temperature of all sky cosmic micro background radiation, right? And taken by WMAP or Wilkinson Microwave Anisotropy Probe, which is one of the instruments specifically designed and sent to the space to measure this cosmic microwave background radiation, right? And what you can see from different colors here is the different temperatures that you have for the cosmic microwave background. And certainly you can see that there are very small changes in the temperature in small regions like that. But if you get the whole sky or the whole picture, we can tell that the cosmic microwave background is uniformly distributed, right? And this cosmic microwave background first discovered in 1960s by two scientists, and we believe that the CMBR is originated in the early universe, and normally this is referred as the echo of the Big Bang, right? And once you correct for different distortions caused by the motion of the equipment and those kind of things, we can tell that cosmic microwave background radiation is highly isotropic, which means regardless of which direction that you are looking at, it looks like the same, right? Now, that is what you can see from this map. And then you may be asking a question that even though I tell that it looks like the same in each and every direction, there are clear signs that you have different temperatures at different locations at certain points, right? It is true there are small variation like here, but look at the value of this variation. You can see that the intrinsic mean intensity of CMBR differs by less than 1 part in 10,000 in different directions, right? So you can see that the difference of this intensity is very, very tiny, which means you can neglect that and then roughly estimate that you will have the same intensity everywhere. So that's why we used to tell that this is a good evidence to claim that the universe is isotropic, right? Right now, from here, I have mentioned that some of the information about the cosmic microwave background here, and what you need to take from this section that I have talked up to here is that, so let me go back and remind you here, as this is a new area for you. So we define basically what cosmology means, and that is basically about the nature, evolution, and the origin of the universe. Let me right. And then when we talk about the large scale structure of the universe, there are four key observed properties that we can first talk, which will help us to understand or build up these theories about the cosmology. And those four key observed properties are: the number one is the dark night sky. So that is what we have already talked, and we talked about the Olbers paradox at under that section. And the second section is cosmological principle that we have talked. And so we basically define what cosmological principle is, and that is basically to tell that the universe is homogeneous and isotropic. And then I explain a little bit more what this homogeneity and isotropy means in the universe. And it is very important to understand that this cosmological principle valid for for the large scale structure of the universe, and I clearly explain it here. And then we have discussed three evidences to tell that the universe is homogeneous and isotropic, right? So that's about the large galaxy surveys, and then 2DF survey devoted to quasars, and then the cosmic microwave background radiation, right? So it is very important that you get these things uh, into your mind and get an idea about what cosmology actually means. And right, so those are the evidences that we have to tell that the universe is isotropic and homogeneous. And since this is the first time that we talk about the cosmic microwave background radiation, so I have, in the previous section, I have mentioned cosmic microwave background radiation as an evidence to tell that the universe is homogeneous and isotropic. By the way, just to let you know that there is a later map than this, which is even more accurate from the results that recently came around 5 to 6 years ago from the Planck satellite, right? So I have not included it here, but just keep that in your mind. There are more accurate results now about this CMBR, which also tells now very clearly that the universe is homogeneous and isotropic according to that results, because the temperature variation that you see in these new results are even less than that what you see here, right? So since we are actually learning about the cosmic micro background radiation for the first time, so I have mentioned here a few some description about how this cosmic microwave background radiation is discovered and what it actually means and those kind of stuff. And right, so up to here, does anybody have any questions before we go into talk about Hubble law and the other observed property, which is about the once again about the cosmic microwave background rate? We have already talked about that. Anybody have any questions up to here?